Hi there, it's Robin. Thank you for joining my presentation on firing partial orders in a Petri Net for the Petri Net Conference 2021. I hope you enjoy. We're at the Petri Net Conference, so we all love Petri Nets, and it's very easy to see why. Because first, they just look nice. They have a formal definition and a very clear semantic. This example is for the presentation, our running example, and the transition names are just A, B, C, D, E, and F. So you already see it's an academic example. And we also allow for arc weights. So we have two arcs weighted with 3 in this example. And now what do I mean with easy semantics? Well, if I give you a so-called firing sequence, which is just a sequence of events where each event is labeled by a transition name, then you can check very easily if this firing sequence is behavior of the Petri net. So the Petri net is in initial marking, and then you take the first event of the firing sequence and you take a look at the related transition A, and then you check all the ingoing arcs, and there need to be enough tokens according to this ingoing arcs in the preset of the transition, and then you call the transition enabled. And if a transition is enabled, it can fire, meaning removing the tokens from the preset and then producing tokens in the places of the post set. So consuming 2 tokens for the ingoing arcs and producing a token for the one outgoing arc. So now A fired, changing the marking of our Petri net, the state of our Petri net, and now we can check the next event, which is labeled by D. So here's D transition. Again, D is enabled, and if D fires, the Petri net reaches this state, this marking. This marking enables now the next event, which is C here. Here you go. We fire C to reach this marking. Then we have another event labeled with A. Again, we already had this transition, now in a different state, also enabled. So we consume the 2 tokens and produce another one. Now we fire the transition B according to the firing sequence, which looks like this. Now we have a second D, also enabled, producing another token here. And the event labeled with E, now there are actually 3 tokens in the preset of E, which is necessary because the weight of the arc is 3 in this example. And now E is enabled, and firing E will remove all the 3 tokens and produce a token in the post set of E. Now finally F is enabled as well. Again, we need 3 tokens. F is enabled, and firing F leads to this marking over here. So all the events of the firing sequence were enabled, so this is valid behavior of our Petri net. We call the firing sequence enabled, and if you have a Petri net and the input to your algorithm is a firing sequence and you want to know if the sequence is enabled, then you just have to execute the sequence from the initial marking and just check. So this algorithm is in linear time. But if you really think that firing sequences are a cool way to model behavior, better stick to state machines. The actual reason we love Petri Net is that they can model distributed systems and concurrent systems. So in this example, if we take a look at transition A and D, they don't share places in their presets, so they don't share resources. So we can fire A and then D, or D then A, or we can even fire both simultaneously, but that's not the point. The actual point is that if transition A lives in the orange house and D lives in the blue house, and we don't know what's going on in the blue and only look at the orange house, we can fire transition A. And the other way around, if we look at the blue house and we don't see what's going on in the orange house, we can fire transition D. And we don't care which one fires first, which was first or second. If they fired simultaneously, we just don't know. We just know they fired independent from each other concurrently without any order. So instead of just looking at firing sequences, we should really look at partial orders. So here we have an example of a partially ordered set of events. We just took the same set of events as before for the firing sequence, and then we removed some arcs to create this partial order. And for the partial order, we only show the skeleton arcs, the so-called Hass diagram. And now every arc can be read as a later than. So the first two events are not ordered, and then the C is after A and the C is after D. And then after the C there is another A and an E, and again these are not ordered and need to be able to be executed concurrently, and so on and so forth. And now the question is, if you have such a partially ordered set of events, how to check if this is enabled in the Petri net. And actually there are algorithms to check, but they're in cubic time. To check if a partial order is in the language of a Petri net, we need to understand the concept of compact token flows. So in this example, let's at first only focus on the yellow place and forget about all the other places. Now, if you consider this place, then every event labeled with A can produce a token, and every event labeled with B or C needs to receive a token. And now we try to find the distribution of tokens so that every event receives enough tokens and no event has to produce more tokens than it's able to. So let's take a look at the first arc. C later than A translates to A can give its token to C. And then we have the arc between the second A and B. Again, B is ordered after A, so A can produce its token and push it to B. So both events, C and B, that needs to have tokens gets their tokens. So this partial order is enabled if we only consider the yellow place. So what about the pink place here? Again, all events labeled with E and D are able to produce a token, and the event labeled F needs to receive 3 tokens. And we need a distribution of tokens so that, again, F gets its tokens and only D, E, and the second D produce 1 token. So the first D pushes its token along this path of relations to F, and E pushes its token to F, and also there's an additional token from the second event labeled with D, and it's pushing its token to F. Now D, D, and E are producing 1 token, and the token flow along the arcs of the relation until they reach F, and F is able to consume all 3 of them. So again, this is enabled for the pink place. And last example is here the green place with the short loops. Here we have a token in the initial marking. So we have a token that can be distributed to the initial events. And then the events labeled with C or D can produce tokens, and they also need to receive tokens. So the initial marking is somewhat free for all, so we can push it to D, and then D pushes a token to C, and this C pushes its token along this path to D, and D consumes this token. And the token D produces, we don't need it anymore. It's a token for the final marking, but every event receives enough tokens, so this partial order is also enabled for the green place. And now it's easy to see that a partial order is enabled if and only if there's a compact token flow for every place. Now, how to decide if there is a compact token flow? Well, we again take a look at our running example in the green place, and we already know that there's a token in the initial marking, and every C and D is able to produce a token and can receive a token. Now we do a translation. So for every event, we create two nodes of a flow network, and we connect the first with the second, and all the other arcs are just given by the partial order. Then we add another node representing the initial marking, which is connected to the initial nodes of a partial order. And then we add a source. And a source is connected to every second node of an event which is able to produce a token, and also to the initial marking. And we add a sink. And the sink is connected to every first node of every event that needs to receive a token. So that's a flow network. And there are so-called maximal flow algorithms which create a maximal flow in these flow networks. And flow just goes from source to sink. So you look for a path from source to sink. And now in this example, there is such a path, so the flow is 1. But there's another path, so we add this path. Now we have 2 paths and a flow of 2. And now there is no path from source to sink anymore, but for flow networks, so here already is flow, but you can take this flow back. In some sense, you find this way of arcs which are not used yet, and you take an arc which is already used backwards, and you have an additional path. You take flow back and connect the first part of the new path with the second path of the old path. So you get altogether 3 paths through the flow network and a flow of 3 in this network, which is a maximal flow in this example. You have a maximal flow of 3, which saturates all the arcs in going to the sink. And this just translates to if you again you remove source and sink, and you translate everything back into events and take a look at the path, at the flow, and just translate it into a token flow, then well, there was a flow of 3 events needed, 1 token each. So this is a compact token flow. And these maximal flow networks algorithms, they are clever ones, and they are in cubic time. For example, the pre-flow push algorithm. So that's known theory. If you have a firing sequence, you can check in linear time if it's in the language of a Petri Net. And if you take a partial order, you can check in cubic time, which is fine, which is quite fast. But if you consider applications where you have lots of behavioral data, for example, in process mining, then, well, linear time is just better than cubic time. So in this presentation and in my paper, we ask ourselves, well, what can be done in linear time for partial orders? What about firing partial orders? And actually, this is a contribution of my paper this year. So we present definitions, proofs, and an algorithm of how to fire partial orders in a Petri Net. We just brute force fire or execute the partial order without looking for a path and without redistribution tokens, and then we see how far we can get with it. So take a look at the example and color all the places. In the first step, we extract the initial marking, which is 2 red, an orange, 2 blue, a green, and purple one. And then we add this marking to the first event, to the first initial event, which is the A. And we create a local marking at A. Then we fire A in its local marking, which is perfectly fine here. Firing A will remove a red and an orange token and will produce a yellow one. So this will create this local marking, and this local marking is pushed to C. Now we have to fire D in its local marking, and its local marking is empty. So D is not enabled because of the green and the purple place. So we have to mark both places, but then we fire D anyways. Firing D brute force in the empty marking leads to one negative purple token and a pink token. So we update the local marking of C. We remove the purple one and add a pink one. And now we fire C in its local marking, which again is fine. Firing C leads to this local marking, a green, three blue, a pink, an orange, and a red one. And this marking again is pushed to the first, just to the first successor of the event. Now we fire A in its local marking, which is fine, producing this local marking. We fire B in its local marking, and then we fire D in its local marking, producing a local marking at F. Now we need to consider the event labeled E. And again, this one needs to be fired in the empty local marking, which is not fine because we need 3 tokens in a blue and there are no tokens. So again, we mark the blue place, but then fire E anyways. Firing E will create -3 blue tokens, and we update the local marking of F. Now again, we fire F, which is fine. We just consume the 3 tokens and produce the final marking. So this is what I call a multi-token flow. A multi-token flow is a local marking at every event, and the set of local markings respect the firing rule and the initial marking. And multi-token flow is always pushed to the first successor of an event. It's not distributed. And now if we have this multi-token flow and we just executed the partial order from start to end, we directly know that there are compact token flows for these 4 places in the example, for the red, the orange, the yellow, and the purple one. The multi-token flow directly relates to a compact token flow. So these places are actually fine. The partial order is enabled for these places. So let's remove them. What about these 3? Well, we cannot conclude that there is no valid token flow because of the following. Well, if we take a look at this event right here, it's forward branching, and there is a multi-token flow for the green and the blue place. So here we had tokens from these 2 colors, and we pushed it to the first successor, but there is a second successor. There could be a redistribution possible. And the same holds for the initial marking. We distributed the tokens from the initial marking to the first initial event, but there is another one. So we cannot conclude there is no compact token flow. So now we have to go on. But it's not a good idea to just try all the different combination of successors, because that's again is redistributing, and that would lead to an algorithm which doesn't run in linear time. So we take a different approach. We already constructed the final marking by firing all the events, and this is unique. That does not depend on the order of execution of the events. So we start from this final marking. We set the Petri net to the final marking, and then we flip all the arcs in the net, and we flip all the arcs in the partial order. And then we fire again, but backwards. So we take the initial marking, the now initial marking, and put it to the first initial event, which is the F. And then we fire F in its local marking, producing this marking and pushing it to its first successor, which is the D in this example. Now we fire E, which is fine. It has an empty preset and produces 3 tokens for C. Then we have to fire D, consuming the green, producing a green and a purple. Then we have to fire a B, producing one green, and then we fire the A, updating the local marking of C. Well, C is enabled and produce a local marking, which is pushed again to its first successor, the A, and now we have to fire D. And we have to fire D in the empty local marking, which is not possible. And it's not possible because of the green place. So we mark the green place and we fire D anyway, producing a purple token for the final marking. And then we see we can fire A, updating the final marking. And now again, we just created a multi-token flow. And this multi-token flow relates to two compact token flows for the blue and the purple place. So these places are fine. The partial order is executable, is enabled for both of these places. So the only thing that's left is this green place. And the reason this green place is difficult is because the event C is forward and backward branching. So there you need luck. If a place is marked at this event, you need a little bit of luck that you by chance find the right distribution. So that's not the case in this example. So what we have to do now to see if this place is enabled is to use the regular token flow flow network compact token flow algorithm and spend cubic time to decide this place. And then we're done. So for 6 of the places, we were able to get a result in linear time by firing forwards and then firing backwards. And so there was only one place left after this procedure, and then we need to spend cubic time to also get a result for this place. And that's just how to fire a partial order in a Petri net. Given is a Petri net, and you input a partial order. And here I cheated a little bit because when you fire the partial order, you need to know also a total order respecting the partial order. So either this is given or you need to calculate it. And then you fire forward. And then for the remaining places, you fire backward. And then you decide enabledness for all the remaining places. And you get the set of valid and the set of non-valid places. And obviously, if all the places are valid, then the partial order is enabled in the Petri net. Now we need to decide if this is helpful or not. So in the paper, I present some experimental results comparing the old algorithm with this just only deciding enabledness with these compact token flows versus firing first and then using compact token flows. And I had a look at the model checking contest of 2020, and the first example is a so-called satellite memory. It's kind of this net structure, and then there are parameters, and you see it's like a lot of arcs, self loops, cyclic behavior, multiple tokens in the markings and stuff like that. So this kind of deal. And then I unfolded randomly generated partial orders of this net, and then I took these partial orders and tried to decide enabledness with the old and with the new algorithm. And the results and the runtimes are in the paper, but you see that here 50% of all the places are simple places. And by simple place, I mean that they can be decided firing forwards or backwards. And the average runtime of this example for both algorithm is quadratic, grows quadratic with the size of the input, with the length of the unfolded partial orders, because you need to distribute tokens, but you don't need to redistribute that much. The structures of the partial orders is relatively easy. And nevertheless, the new algorithm firing first is twice as fast as the old one, which directly relates to the number of simple places. Then I had a look at the process discovery contest of 2020, And here you can see the master model, which is then given in different variants, dependent on if you want to have dependent task loops, routing constructs, etc. So again, different instances of this model. And the picture is actually a little bit misleading because there are no token yet in the model. It's just a typical workflow net going from left to right with one token in the initial and then eventually a token in the final marking. And the colors just depend to the different variants. And the numbers are just the names of the nodes. But again, I took the different variants and then I unfolded it to randomly generate partial orders, and then I put them back into the old and the new algorithm and compared their runtime. And like you have for workflow nets, they tend to have small markings because there's one token in the first place, and there will be hopefully one token in the final place at the end if everything is sound. And this leads for the algorithm when you fire, even if events are branching, most of the places are just empty. Um, in this example, actually 99% of all the places were simple places. So firing just did the job. And the average runtime of the old algorithm again is quadratic. So you need to calculate the distribution of token, but you don't have to redistribute. Uh, it just behaves quadratic in this example. And the new algorithm is much, much faster. Again, please have a look at the paper for the actual runtimes. And if you have an application, let's say process discovery or stuff like that, where, well, ignoring 1% of the places is actually fine, then the runtime of the new algorithm is actually in linear runtime, because firing forward then backward just decides 99% of all the places. And that concludes my talk. Thanks a lot.